So this is chapter 15.4, the Boltzmann's constant. So Boltzmann was an Austrian physicist and he worked on statistical mechanics and physics. He applied Newton's laws to explain the behavior of gases. Um, and then you got the variables, temperature, pressure, and volume. He linked the microscopic properties and the macroscopic properties together with relationships. And there is a constant named after him, Boltzmann's constant, and the equation for that is the molar constant is equal to Boltzmann's constant times Avogadro's number. So if you rearrange to get K, you should get 1.38 times 10 to the minus 23. So Boltzmann's constant is 1.38 times 10 to the minus 23. And the molar gas constant is 8.31. Avogadro's number is 6.022 times 10 to the 23. Okay, so you got the equation. Boltzmann's constant is equal to R divided by capital NA, or R is equal to K times capital NA. You should have seen these three equations. PV equals nRT, PV equals nKT, PV equals small n, big R times T, PV equals big N times K times T. And the one at the bottom, you've got the number of particles is equal to the number of moles times Avogadro's number. So if you remember that 1 mole has 6.022 times 10 to the 23. So to get the number of moles, you divide the number of particles by Avogadro's number. So n number of moles is equal to number of atoms or molecules divided by Avogadro's number 6.02 times 10 to the 23. Alright, so let's have a look at this example. So you have a large school classroom that is large and massive, that is not small or tiny, has dimensions 15 meters by 10 meters by 4 meters. On a typical winter's day, the atmospheric pressure is about 100 kilopascals and the temperature is about 18 degrees Celsius. Calculate the number of particles and the number of moles of gas in the large classroom. So we're going to use PV equals big N KT. Rearrange for the number of particles, big N, you get PV divided by KT. So you know that the pressure is 100,000 because kilopascals is 1,000. 100,000 pascals times, and then times the volume, which is 15 times 10 times 4, divided by K, which is Boltzmann's constant, which is 1.38 times 10 to the minus 23. And remember, you got to convert the Celsius into Kelvin, so you add 273. Once you put all that into a calculator, you should get N as 1.494 times 10 to the 28 particles. And then to find the number of moles, you use this equation and you divide by 6.022 times 10 to the 23, and you should get 2.48 times 10 to the 4 moles. Right, this slide is the derivation for PV equals a third mn v squared, or you can have P is equal to a third times the density times v squared. Alright, so let's combine the PV equals a third nmc squared and nkt, put them two together, and then divide both sides by n because they're common. And then we need to make one of the sides half mv squared because we want to equate one side is the kinetic energy. So if you times the left hand side by 3 over 2, you want to get rid of the 3, don't you? So then you have half mv squared equals 3 over 2 kt. So the mean average kinetic energy of the particles in the gas is 3 over 2 kt. And it's about the particles. So let's have a look at an example. The mass of atomic oxygen is 2.66 times 10 to the minus 26 kilograms. So the molecular mass is 5.32 times 10 to the minus 26 kilograms. Because you know that oxygen is diatomic, O2. So if one of the oxygen is 2.66 times 10 to the minus 26, you times it by 2. Calculate the root mean square speed of molecular oxygen gas at 20 degrees. So you use the equation kinetic energy is 3 over 2 kT. Rearrange because you know that kinetic energy is half mv squared, but we're using the root mean square in this case. So the 2's cancel out because it's at the bottom of the fraction. You end up with 3 kt. Divide by m to get c squared, and then you square root that. You get the root mean square. So the equation for root mean square is 3 kt divided by m, and then you square root it, and you know that k is 1.3806485 times 10 to the minus 23. You substitute the t with 20 plus 273 because you remember you've got to convert that to Kelvin. So t is equal to 293. You know that m is the molecular mass, which is 5.32 times 10 to the minus 26. And then you know get k. So when you put that into the equation, you should get around 477.5 meters per second. Right, you need to know three terms. The most probable speed of gas molecules, described by the Maxwell-Boltzmann distribution, is the speed at which the distribution graph reaches its maximum. The average speed of the molecules is the mean of all the magnitudes of velocity at which the molecules of the given gas are moving. And then the root mean square speed of the molecules is the speed at which all the molecules have the same total kinetic energy. Alright, so if let's just say you've got a temperature T1, different gases will have the same average kinetic energy because the definition of temperature is the measure of the average kinetic energy. So if they have the same temperature, they should have the average kinetic energy. Now, even if you have different gases, for example, if you have a gas of oxygen and you have a gas of helium, they are both at the same temperature, they both have the same average kinetic energy, even if they have different masses. However, they will have different root mean square speeds because of the equation, because of this equation, 3 kt over m square rooted. So their root mean square speeds will be different. For example, you've got helium atoms and oxygen atoms. Which one is lighter? The helium atoms will have lower masses. So if you look at the equation again, if m is small, then c is big. So helium atoms will have lower masses, you have higher root mean square speed, and then some of the faster moving helium atoms will escape the Earth's atmosphere. If you look at this diagram here, for example, if you have increasing mass, so as you have heavier compounds, then because m increases, assuming that t stays the same, then the root mean square speed will increase for sorry, if m increases, then the root mean square speed will decrease. So the bigger the mass, the lower the root mean square speed. So if you look at the graph on the left hand side, helium has less mass than xenon. Can you see that the graph is squashed, but the speed will be higher. So the maximum speed will be higher compared to nitrogen and xenon. So the bigger the mass, the lower the root mean square speed. Now let's talk about the internal energy of a gas. Now the definition of internal energy of a gas is the sum of the potential energies and the random kinetic energies of all the particles. So because it's a gas, the distances between each of those particles will be very big. So it is negligible. There will be negligible electrostatic forces between the particles, except when they're colliding. Because when they're colliding, they're touching, aren't they? So the first assumption is that it is negligible electrostatic forces in a gas. Number two, there's zero electrical potential energy in an ideal gas. This comes from number one, because obviously in an ideal gas, the distances between the particles are big compared to the actual particle. Therefore, because from the definition of internal energy, they only have kinetic energy because potential energy is zero. So therefore, if you double the thermodynamic temperature, which is measured in Kelvin, it will double the kinetic energy and therefore the internal energy because the potential energy is equal to zero.